I am E20302 and I am going to present the progress of my project. So my project title is Development of a Hydrogen-based direct reduction system for iron production supervised by Dr. I.W. Kularatne. This is the content of my presentation. Let's go through the background of my project. The Buttal deposit is a high-grade iron ore deposit resource located in Monalagala district covering a large surface area. It has a high iron content, which hematite percentage as an average 78.84% and maximum is about 89.5% that remains untapped. Up to now, nobody has experimentally demonstrated a practical low-carbon reduction route specifically for Buttala iron ore, so there is no validated economically viable green process for this local deposit. Let's see the environmental challenges with conventional carbon-based reduction. Conventional blast furnace iron making is highly carbon dioxide intensive, emitting roughly 1.85 tons of carbon dioxide for every ton of steel, with more than 70% of those emissions coming from the blast furnace itself because coke is used both as the fuel and the reducing agent. In contrast, hydrogen-based reduction combined with an electric arc furnace can reduce direct carbon dioxide emission by about 85 to 97%. And if the hydrogen is produced from renewable energy, such as solar-powered electrolysis, the entire iron production route can approach almost zero net carbon emission. Let's go through the research gap of my project. Most existing work on the Buttal iron ore deposit is limited to mineralogical, chemical, and economic characterization, and there are essentially no studies that actually perform iron making or reduction trials. In particular, I could not find any published work that experimentally demonstrate direct hydrogen reduction of Buttal iron ore at lab scale, so this project aims to fill that gap. So, according to the background of my project, aims to design, build, and experimentally validate a lab-scale solar-powered hydrogen reduction system that produces metallic iron from local Buttal iron ore by integrating an alkaline water electrolyzer with a rotating ceramic reactor and demonstrating Buttal ore's suitability for a low-carbon iron-making route. Let me now show you the overall concept of my project. As you can see, the system is consists of four main subsystems. First, the solar unit, which provides renewable electrical power to the electrolyzer. This ensures that the entire process is green and low carbon. Second, the hydrogen generation unit, an alkaline water electrolyzer where water is split into hydrogen and oxygen. The hydrogen produced here is the key reducing agent for our iron ore. Third, the rotating reduction reactor. The tube rotates continuously to improve contact between the ore and the hydrogen gas, and it is heated to about 500 to 540 degrees Celsius using an induction coil wound around the tube. Fourth, the induction heating system, which supplies the thermal energy needed to drive the reduction reaction inside the rotating tube. This is a direct reduction route where hydrogen removes oxygen from the iron ore, producing metallic iron and water vapor with zero carbon dioxide emission. Here, I discuss the technical feasibility of the proposed system. First, material availability is confirmed. Buttala iron ore can be sourced locally and existing crushing facilities allow to prepare it as a fine powder suitable for reduction experiments. Second, I checked the theoretical limits of the electrolyzer. The reversible cell voltage for water splitting is about 1.23 volt and the thermoneutral voltage is about 1.48 volt at 25 degrees Celsius, which defines the fundamental lower bound for our cell operation. In practice, I operate around 2 volt, which is realistic for alkaline cell. Also, the operating conditions are achievable. For 20 grams of Buttala iron ore, the stoichiometric hydrogen requirement is around 7.6 liters and my design electrolyzer power supply combination can comfortably generate this volume within the planned reaction time. Fourth, hydrogen purity is adequate for this reduction. A simple zeolite-based purification stage removes moisture and residual electrolyte droplets so that the gas entering the reactor is dry, reduction-grade hydrogen. Finally, The setup provides measurable outputs. We can monitor hydrogen flow rate, electrical power consumption, or mass loss, and degree of reduction, which allows to quantitatively evaluate the performance of the process. I also carried out a process simulation using DWSIM for one operating case. The main purpose of this simulation was to check whether the system can realistically deliver the hydrogen flow rate I need for the reactor. For this case, the DWSIM results show that a 10 kilogram per hour water feed would produce approximately 2.9 liters of hydrogen per hour under the specified conditions. Since I am still in the design stage and all parameters are not yet finalized, I use this software case mainly as a feasibility check rather than as a final operating point. The result shows that with a 10 kilogram per hour water feed, I can already get about 2.9 liters per hour of hydrogen. So by adjusting variables such as current, density, cell area, water feed rate, I have enough flexibility to reach the exact hydrogen flow rate required by my rotating reactor. This slide shows the overall project plan divided into four phases. First, in the design phase, I calculate the power requirement for the whole system and then design each subsystem. Second, in the implementation phase, I will develop and fabricate the hydrogen-based direct reduction system according to the design. Third, in the testing phase, I will operate the complete prototype, check for leaks, temperature control, and stable hydrogen flow, and then modify the design if any issues appear. Finally, in the evaluation phase, I will analyze performance in terms of hydrogen utilization efficiency, energy consumption, and carbon footprint compared to conventional steelmaking routes. This is the detailed project timeline. Now I am in the design phase. This slide shows the some of the key findings from the design phase of the hydrogen generation unit. In this project, I have employed several adapted innovative methods. First, rotating ceramic tube reactor with induction heating. I adapted the conventional fixed bed reduction reactor concept into a rotating ceramic tube that is heated to 500 using an induction coil. This allows continuous tumbling of O particles for better hydrogen contact and more uniform reduction compared to static beds. Next, direct integration of on-site hydrogen production with reduction reactor. Instead of using bottled or stored hydrogen, I directly couple an alkaline water electrolyzer to the reduction reactor. This eliminates storage and transport risk and makes the process suitable for small-scale decentralized green iron production. Next, zeolite-based hydrogen purification. I incorporate a simple zeolite molecular sieve dryer downstream of the electrolyzer to remove moisture and impurities. That's all for the presentation. Thank you.